Hello and welcome to G Fun Facts Online. Our sun, it feels familiar, doesn't it? A steady, life-giving orb hanging in our sky. But that serene image is a comforting illusion. In reality, our star is a dynamic, turbulent nuclear furnace, a cauldron of extreme physics that periodically unleashes torrents of matter and energy at incredible speeds. These are the sun's superfast eruptions, and at their core, they turn our star into a colossal particle accelerator, one that dwarfs any machine ever built on Earth. These eruptions fling vast clouds of solar material, protons, electrons, and heavy ions into space at near the speed of light. They are the drivers of space weather, a celestial force that can paint our skies with breathtaking auroras, but also threaten to cripple our advanced technological civilization. For decades, scientists have puzzled over a fundamental question. What process can take a simple particle and accelerate it to a velocity that crosses the 93 million miles to Earth in less than an hour? Today, we're journeying into the heart of our star's eruptive nature to find out. We will unmask the physics of its solar particle accelerators, from the tangled magnetic fields that store immense energy to the explosive release that powers them. We'll explore the two primary engines of this acceleration, the blinding flash of a solar flare and the titanic expulsion of a coronal mass ejection. We'll see how modern robotic explorers are revolutionizing our understanding. And finally, we will confront the profound implications of these eruptions, from their impact on our daily technology to the ghostly records of ancient, terrifying superflares hidden in the rings of ancient trees. Let's start with one of the most spectacular events in the solar system, the solar flare. A flare is a sudden, intense burst of electromagnetic radiation in the sun's atmosphere, releasing energy equivalent to millions of hydrogen bombs exploding at once. From Earth, we see this as a rapid brightening. The most powerful flares can completely saturate the detectors of our sun-observing spacecraft. For about 8 minutes, the time it takes for light to travel from the sun, the energy from a flare bathes our side of the planet. While our atmosphere protects us from the most harmful X-rays, this energy can have immediate effects, like disrupting high-frequency radio communications. But what powers such a ferocious release? The answer is magnetism. The sun isn't a solid body. It's a giant ball of electrically charged gas called plasma. This plasma is in constant, churning motion. The sun also rotates differentially, meaning its equator spins faster than its poles. This churning and twisting motion drags and contorts the sun's magnetic field lines, storing immense amounts of potential energy, like thousands of twisted rubber bands. This is most pronounced in what we call active regions, which appear as sunspots. It is here that the stage is set for a flare. The explosive energy release is driven by a process called magnetic reconnection. This happens when oppositely directed magnetic field lines are forced together. Under immense stress, they can suddenly snap and reconfigure into a new, simpler, lower energy arrangement. The lost magnetic energy doesn't just vanish. It's catastrophically converted into intense heat and the kinetic energy of surrounding particles. For decades, a puzzle was how this could happen so quickly. Theory suggested it should be a slow process. But recent research, aided by missions like NASA's Magnetospheric Multiscale, or MMS, has shown that complex dynamics within the reconnection zone, including the formation of small magnetic bubbles called plasmoids, can dramatically speed up the process. This act of magnetic reconnection itself is a potent particle accelerator. The collapsing magnetic fields create powerful electric fields that grab charged particles, mostly electrons, and accelerate them to tremendous speeds in short, sharp bursts. This is the source of what we call impulsive solar energetic particle, or SEP, events. These impulsive events are electron-rich, and they have strange isotopic signatures, like a 10,000-fold increase in a rare isotope of helium. They are also linked to Type 3 radio bursts, a characteristic radio whistle created by the escaping electrons. In a typical flare, most of these accelerated particles are trapped in magnetic loops and slam back down into the sun, releasing the radiation we see as the flare. But if the reconnection happens on open magnetic field lines that stretch into space, a fraction of these particles can escape, becoming the first harbingers of a solar eruption to reach Earth. While a flare is a brilliant flash of light, a coronal mass ejection, or CME, is an act of brute force. It's a colossal expulsion of plasma and magnetic field from the sun's corona. A single CME can blast billions of tons of solar material into space at speeds up to 3,000 kilometers per second. The fastest CMEs can cross the Sun-Earth distance in just 15 to 18 hours. Flares and CMEs often happen together as part of the same eruptive event. They are both rooted in magnetic instability, but they are fundamentally different. A flare is a release of radiation. A CME is the physical ejection of matter. The true power of a CME as a particle accelerator comes from its journey through space. A fast CME plowing through the slower ambient solar wind creates an enormous shock wave in front of it, like a supersonic jet. This shock wave is the dominant mechanism for producing the most intense and dangerous type of solar particle events, known as gradual events. The process at play is called diffusive shock acceleration. Imagine a charged particle upstream of this shock. It crosses the shock front into the turbulent region behind it. The tangled magnetic fields then scatter the particle and send it back across the shock. Each time the particle crosses the shock front, it gets an energy boost, like a tennis ball being hit back and forth between two approaching rackets. The particle can be reflected back and forth across the shock numerous times, gaining huge amounts of energy with each crossing. This process is incredibly efficient and can accelerate particles to billions of electron volts. There is a catch, however, called the injection problem. This acceleration process works best on particles that already have some energy. It needs a seed population of energized particles to work on. One leading theory is that these seeds are supplied by smaller, preceding impulsive flare events. In this scenario, the flare provides the initial kick, and the CME-driven shock provides the main, sustained acceleration. The resulting gradual events are proton-rich, widespread, and produce the highest overall particle intensities, posing the most significant radiation hazard to astronauts and spacecraft. For many years, the origin of these large particle events was fiercely debated. Because they were often accompanied by dramatic flares, many scientists assumed the flare was the source of all the particles. This period was even called the era of the solar flare myth. Disentangling the contributions of the flare's reconnection from the CME's shockwave was a huge challenge. It took decades of observations from multiple spacecraft, analyzing the composition, timing, and distribution of particles, to build the case that flares and CMEs drive two distinct types of particle acceleration. The final confirmation of this two-part paradigm came from a new generation of solar observatories, most notably the European Space Agency's Solar Orbiter. Launched in 2020, Solar Orbiter has a unique elliptical orbit that takes it incredibly close to the Sun, while also carrying a sophisticated suite of 10 instruments. Some are remote sensing instruments, like telescopes, that watch the Sun from a distance. Others are in situ instruments that measure the particles and magnetic fields flowing directly over the spacecraft. This combination is a game changer. It can simultaneously watch a flare erupt on the Sun's surface and measure the resulting stream of electrons as they arrive. Between 2020 and 2022, Solar Orbiter observed over 300 solar energetic electron events. The data revealed a definitive split: quick, short bursts of electrons directly linked to the X-ray signatures of solar flares, and broader, longer-lasting swells of particles associated with the passage of large CMEs. By flying so close, Solar Orbiter could measure these particles in a pristine state, before their long journey could erase the signatures of their origin, allowing scientists to trace them back to their source. Our profound new understanding is a direct result of sending robotic emissaries into one of the most hostile environments in our solar system. Leading the charge are two missions: NASA's Parker Solar Probe and ESA's Solar Orbiter. Launched in 2018, the Parker Solar Probe has a mission straight out of science fiction: to fly through the Sun's outer atmosphere and touch the Sun. It's the fastest human-made object ever, protected by a revolutionary carbon composite heat shield that withstands temperatures of nearly 500 degrees Fahrenheit. Behind this shield, its instruments directly measure the electric and magnetic fields, count the particles in the solar wind, and even take pictures of structures like CMEs before the spacecraft flies through them. In its daring journey, Parker has already made landmark discoveries. It has flown through the corona, confirming it touched the Sun in 2021. It has discovered bizarre magnetic switchbacks, sudden S-shaped reversals in the magnetic field that might be key to understanding how the solar wind is heated. While Parker gets up close and personal, Solar Orbiter gets the bigger picture. The two missions work together, sometimes aligning so that Parker flies through a stream of solar wind previously observed by Solar Orbiter, giving us a complete three-dimensional view of solar eruptions. But a particle's journey from the Sun to the Earth is not a simple straight line. Interplanetary space is filled with the solar wind, a continuous outflow of magnetized plasma. This turbulent sea of magnetic fluctuations scatters the particles, dramatically altering their paths. This is known as perpendicular diffusion, and it helps explain why particles from a single eruption on one side of the Sun can still be detected at Earth, even if we weren't in the direct line of fire. Accurately predicting the arrival time and intensity of an event at Earth requires modeling not just the acceleration at the Sun, but also this chaotic, scattering-filled journey through 93 million miles of turbulent space. When these particles finally do reach us, their impact can be profound. The beautiful glow of the aurora is a direct consequence of these particles striking our upper atmosphere, but this beautiful display is a symptom of a much more powerful phenomenon: space weather. High-velocity particles can damage satellites, degrading their solar panels and frying their electronics. They can disrupt radio communications and interfere with GPS signals. For aircraft flying high-altitude polar routes, they pose a radiation hazard, forcing flights to be rerouted. But perhaps the biggest threat is to our power grids. A CME carries a powerful magnetic field that can induce strong electrical currents on the ground. These currents can flow through power lines, overloading transformers, and potentially causing widespread, cascading blackouts. To understand the worst-case scenario, we look to September 1859, the Carrington event, the most intense geomagnetic storm in recorded history, struck the Earth. Auroras were so bright people could read newspapers by their light at midnight. The world's most advanced technology at the time, the telegraph system, was thrown into chaos. Telegraph pylons threw sparks, and some systems kept running even after being disconnected from their power. A storm of that magnitude today would be a multi-trillion-dollar catastrophe, crippling transportation, finance, and food and water distribution. The Carrington event is a stark reminder of what the Sun is capable of, but could it be even worse? Evidence has emerged that our Sun can produce eruptions on a scale that is difficult to comprehend. This evidence comes from an unlikely witness: ancient trees. Trees absorb a radioactive isotope, carbon-14, from the atmosphere, preserving it in their annual growth rings. This gives us a record of cosmic ray intensity stretching back thousands of years. In 2012, while studying ancient Japanese cedar trees, a student named Fusa Miyake discovered something astonishing. In the ring for the year 774 AD, there was a sudden dramatic spike in carbon-14, about 20 times greater than normal. The cause? An unimaginably powerful burst of solar, energetic particles from our own Sun. These massive radiocarbon spikes are now known as Miyake events. Several have now been identified, including a colossal event 14 300 years ago that was an order of magnitude larger than the Carrington event. The message from the trees is clear. Our Sun is capable of producing particle events far beyond anything we have directly observed. The existence of Miyake events fundamentally raises the stakes for space weather forecasting. Despite this incredible progress, the Sun still holds many secrets. One of the most enduring is the coronal heating problem. The Sun's visible surface is about 6,000 degrees Celsius, but its outer atmosphere, the corona, sizzles at over 1,000,000 degrees. How? A leading theory points to nanoflares, a perpetual storm of tiny explosive energy releases, each about 1/1000th the size of a regular flare, all powered by the same magnetic reconnection process. The idea is that the corona is heated by the collective popping of trillions of these microscopic explosions. Other questions remain. We still don't fully understand the injection problem for shock acceleration, and predicting exactly when an active region will erupt remains a huge challenge. The quest to understand the Sun's superfast eruptions is entering a golden age. We have probes flying through the very regions where these particles are born. We have telescopes that see the Sun in unprecedented detail, and we have echoes from ancient trees, reminding us of the Sun's awesome potential. Unmasking our star's powerful particle accelerators is more than a quest to understand a distant star. It's a journey to understand the fundamental physics of our universe, and a vital step in protecting our fragile, technological world from the fury of its nearest celestial neighbor. The Sun gives us life, but it also commands our respect. Thanks for listening to G Fun Facts Online.